Hello everybody, and welcome to exercise 2 on page 87 of the workbook. Hopefully you've given this exercise an attempt on your own, and in this video we're just going to talk through a part of it, okay, just so you can kind of compare to what you did, and if you got stuck in various places, this might give you some insight into how to finish the problem. Okay, so let's read this together. So given below are several abelian groups of order 360, so every group on this list has 360 elements in it, and they ask us how many different isomorphism classes are represented. Okay, basically how many of these groups are really different, and then to identify any groups on the list that are isomorphic. Okay, so there's kind of a lot to do here, and I'd like to start by just seeing if we can spot some groups on this list that are isomorphic. Okay, maybe give some brief reasons. So for example, if we start with Z360, the very first one on our list, I claim that that's isomorphic to Z5 plus Z12, or I'm sorry, not Z12, Z72, which in turn is isomorphic to Z5 plus Z8 plus Z9. Okay, now how do we know all of that? Okay, well, this really comes back to theorems that were talked about earlier in the course. So if you take the first two groups on the list, those are isomorphic because of the fact that the GCD of 5 and 72 is 1. They're relatively prime to each other. And we have a theorem that says that when that's the case, together with the fact that 5 times 72 is 360, tells us that Z360 is isomorphic to Z5 plus Z12. Okay, we could make a similar argument for the other isomorphism. Okay, the GCD of 5, 8, and 9, that's also 1. Okay, and so we decompose it as Z5 plus Z8 plus Z9, that also has to be isomorphic to Z360. Okay, so we're just using some theorems that we talked about earlier. Okay, and kind of continuing down here, let's see if we can spot some other things that are isomorphic. I claim, for example, that Z36 plus Z10, that's one of the groups on this list, that's actually isomorphic to Z2 plus Z4 plus Z5 plus Z9. Okay, well, where did that come from? Okay, well, you can kind of reason that out by just looking at the right-hand side and putting some things together. So for example, take the Z4 plus the Z9. 4 and 9 are relatively prime. So if you put the Z4 and the Z9 together, they would have to be isomorphic to Z36. Okay, so because Z4 plus Z9 is isomorphic to Z36, and if you look at the other two terms, Z2 plus Z5, 2 and 5 are relatively prime, so Z2 plus Z5 is isomorphic to Z10. Okay, so it kind of, that isomorphism comes from just looking at the right-hand side and grouping some things together, essentially, that we can. Okay, and let's see, let's mention another one. Okay, so I claim that Z5 plus Z6 plus Z12 is actually isomorphic to Z2 plus Z3 plus Z60. Okay, we can give kind of a similar reason for that. Okay, so the 2 and the 3, 2 and 3 are relatively prime, so we can put that Z2 plus Z3 together into a Z6, which we're seeing over here. Okay, and then the other thing we might notice is that on the other side, Z5 and Z12, 5 and 12 are relatively prime, and so that direct product is going to be isomorphic to Z60. Okay, and one last pair of isomorphisms here. I claim that Z6 plus Z6 plus Z10 is isomorphic to z2 plus z2 plus z3 plus z30. Okay, now why is that true? Okay, well what we can do is maybe, let's start with what we've got on the right-hand side and just see if we can break it down, convince ourselves that it's really isomorphic to the left-hand side. Okay, so one thing we could maybe do is to notice that the z2 and the z3, we can put those together into a z6, okay, because 2 and 3 are relatively prime. Okay, and what else? Oh, and actually one other thing that we could do, maybe just to save a little space at the same time, the z30 that you see here, we could pull that apart and do a z6 plus a z5. Let's do that. Okay, because 6 and 5 are relatively prime. All right, and then notice that we can put the 2 and the 5 together, okay, because 2 and 5 are relatively prime. That's going to give us a z10 plus a z6 plus a z6. Okay, and that's isomorphic to what we have over here on the left-hand side. Remember, again, the order doesn't matter here. It's just the number of pieces and the size of the pieces. Okay, so my claim is there are 4 different isomorphism classes. Okay, I'm just going to circle them one by one. I'm hoping you're a little bit skeptical of that, though, a little bit worried about me just jumping to that conclusion. So I've kind of given you some insight as to why some of these groups are isomorphic, but I don't think I've said anything about how we know that the groups in each of these 4 classes are really different from each other. Okay, so we'd have to do a little bit more here to convince ourselves that we've really got 4 different isomorphism classes here. Okay, now I don't want to go through the entire argument, but let's talk through maybe part of it. Okay, so what if we wanted to show that these 2 isomorphism classes are really different? That would involve taking a group or a representation from each class and giving some sort of an argument why those 2 groups that I've circled are different from each other. Okay, let's talk about that. I'm going to change pages on you here and go to a blank page. Okay, and you'll notice that I've just recopied those 2 groups that we circled. We're going to try to think about why those groups are really different. And the main tool that we have that would allow us to make that determination is to go back to theorem 1.11, I think it was, or I'm sorry, not 1.11, 11.1, the fundamental theorem of finite abelian groups. Okay, and it says that the way that you can tell whether they're isomorphic or not is to kind of write them in the standard form that the theorem says. We'd like to write them as a direct sum of Zn, where n is a prime power. Okay, notice first that the first of the 2 groups is already in the correct form. Okay, and we can emphasize it by maybe rewriting it like this. Z of 2 to the first plus Z of 2 to the second, because 4 is 2 squared, plus Z of 5 to the first, plus Z of 9 is 3 squared. Notice that every single one of the n's has the form of a prime power. That's the form that we want it to be in, okay, so that we can apply theorem 11.1. Okay, and then we're going to move down to the second one and see if we can write it in the standard form. Okay, so we've got Z to the 2 to the first. Okay, Z to the 3 to the first, those are okay. 2 to the first and 3 to the first are prime powers, but 60, that's not in the form of a prime power, so we're going to have to do a little bit of work there. So how about if we first break it down into Z12 plus Z5? Okay, we can do that because the GCD of 12 and 5 is 1. Okay, and then 12, let's see, if we break that down, that's 2 squared times 3. Okay, 5 is already a prime to the first power, so we're just going to go one more step here and break down that 12 as Z to the 2 squared plus Z to the 3 to the first. Okay, can we really get away with doing that? We can, because 2 squared and 3 to the first, those are relatively prime. Okay, so if you take their direct product, it's going to be equal to z12. All right, and so what we need to compare then is this and this. Okay, those are both in the form of theorem 11.1, and notice that the number of factors is different. Okay, up here we've got 4 terms, and down here we've got 5 terms, and so the fundamental theorem of finite abelian groups tells us that these can't be isomorphic because the number of terms doesn't match. Okay, and so what I would challenge you to do then is to go back, okay, to the example and just play that game with each of the 4 isomorphism classes. You should be able to take a representation from any 2 of these and come up with a reason, like we just did, why the groups in those classes are not isomorphic to each other.